This video is going to introduce you to the concept of Faraday's law of electrolysis, and the next couple of videos after this will show you some calculations involved. But first, let's get into Faraday's law of electrolysis. Faraday actually had a couple of laws, so this is one we're interested in at this stage. And we sort of want to go back to something we looked at previously, and that is stoichiometry and the mole. And then we're going to tie that in, based on Faraday's law, to electrochemistry. So we're going to look at, just remind you of this concept of a chemical equation and a balanced chemical equation. So we're going to balance this first. So to balance this, I'm going to make that 2 times H2, 1 times O2, and 2 times H2O. So what does that equation actually tell us? Well, we can look at this at the atomic level. And at the atomic level, what we're looking at here is 2 molecules of hydrogen plus 1 molecule of oxygen. We yield 2 molecules of water. Okay, so that's pretty straightforward. Well, we can also look at this at the level of the mole, and this is something we studied a lot. 2 moles. The 2 tells us moles. These ratios are what are very important. So 2 moles of hydrogen and 1 mole of oxygen yield 2 moles of water. And so it's that molar level, and so what we now have is N converted to a mass, and we can do that using the molar mass. And so that those ratios are really a link between an amount in moles and a mass in grams, which is what we really need to look at things in, a mass in grams. Okay, so the balanced chemical equation is important because it gives us those ratios. Those ratios could be between molecules, atoms, ions, anything, subatomic particles. And using these ratios, we could solve a variety of problems dealing with mass, volume, and concentration. Okay, and so just wanted to quickly remind you that. So as a quick historical aside, I just want to tell you a little bit about the electron. So J.J. Thomson is credited with the discovery of the electron, and by 1902 it had been determined that the charge of a single electron was about 10 to the minus 19 coulombs. Okay, so a very small charge. You wouldn't expect it. It's an exceptionally small electrical particle. Robert Millikan took on the task of better determining the charge of an electron, and he undertook what is now considered a classic experiment. It's called the oil drop experiment. Basically, he was able to suspend an electron in between 2 magnetic fields, and because he knew the field strength and the mass of the electron, he could determine the charge on that electron. That is, the charge is based on the amount of charge needed to hold it suspended. And so that was it was a very clever bit of work, and he established a charge that has since that time only been bettered by less than 1%. And so this is now considered to be the acceptable charge for the charge of a single electron, 1.60217733 times 10 to the minus 19 coulombs. So Millikan won a Nobel Prize for his efforts. As I said, this is considered a classic chemistry experiment, not only for the design of it, but also for the exceptional precision that Millikan was able to carry out those experiments with. All right, so remember that number, the charge of a single electron. We're going to come back to that. Okay, so here's another balanced equation. And so you should recognize that balanced equation. Copper 2 plus 2 electrons yields copper solid. That is a reduction. The reduction of copper ions. Copper 2 ions. So, again, in terms of stoichiometry, we can look at this as a single ion plus 2 electrons yields a single atom of copper solid. And now we're back to moles. So we can look at that as 1 mole of ions plus 2 moles of electrons yields 1 mole of an atom. And so now we have, again, a link between a molar amount, and here's an atom, ions, they have mass, and a charge. This is charge. Charge here, we can look at this as linked to mass because we have the moles. And so that, in a nutshell, is really the power of Faraday's law. So Faraday's law can be stated as follows. The amount of a substance, N, consumed or produced at one of the electrons in an electrolytic cell is directly proportional to the amount of electricity that passes through that cell. That is, N is directly proportional to Q. And so what is N? Well, you should know that. number of moles. And what is Q? This is the charge or current that passes through the electrolytic cell, that is applied to the electrolytic cell. So that's Faraday's law. So basically look at Faraday's law as a link between the charge in terms of electrons that are transferred and a mass, and that could be mass of ions in the solution, mass of atoms that are produced or utilized if the electrode's being utilized. Okay? So let's go over a few specifics first. So the flow of electrons through an external circuit is referred to as electrical current. So flow of electrons is current, has a symbol I, capital I, with the units of amperes, capital A. So 1 ampere is equivalent to the flow of 1 coulomb of charge through a circuit in 1 second. So an ampere equals coulomb per second. And so remember, ampere is the unit for current, coulomb is a unit for charge, second is a unit for time. So current I equals Q over T. And this is important. This is a very useful little equation, and we can rearrange it in several different iterations. So one other iteration would be that the charge, total charge Q, equals current I times T. So if we know a current and a time, we can determine the total charge. Or if we want to, we can find T. T equals Q divided by I. So just like molar mass, just like molar volume of gas, if you remember the units for ampere, coulomb per second, you have this ready-built little equation that you can then manipulate. And as I mentioned before, the charge on a single electron, one accepted number there, and we've shortened it a little bit, 1.6022 times 10 to the minus 19 coulombs. Okay? Now, one last thing. Charge on a mole of electrons. Okay? So charge on a mole of electrons, well, how are we going to determine that? Well, it's pretty straightforward. We just take the charge of 1 electron, which we just found out, times the Avogadro constant, Na. And so there's the charge on 1 electron, 1.602 times 10 to the minus 19 coulombs per 1 electron, times the Avogadro constant, 6.022 times 10 to the 23rd electrons per mole. So what's the answer? Well, there is the charge on a mole of electrons. So if we go back to our equation, Cu2 plus 2 electrons yields Cu solid. Here's a link. Moles of electrons, 2 of them, and there's the charge on 1 mole of electrons. And so that allows us to convert from a charge or a current to a mass. Either way, we can determine the mass of the ions or the mass of the solid that we have. And so that is what we're really going to be able to do with this number. And this number is known as the Faraday, capital F. And it's a constant. And so it's not a number you have to remember, but it is a number you have to be able to use. And so when do you have to be able to use it? Well, after you watch the next videos that go through a couple of samples where we use the Faraday and other techniques to solve some problems. So that concludes this video.